Welcome back to Basic Electronics. In this lecture, we will discuss a very important issue in electronics, namely common mode and differential mode voltages. We will then look at a related figure of merit for amplifiers, namely the common mode rejection ratio or CMRR. We will look at an op-amp circuit called the difference amplifier, which can be used to amplify the difference between two input voltages Vi1 and Vi2. So let us begin. Let us now begin our discussion about a very important topic in electronics, and that is common mode and differential mode voltages or signals. And we will do that with respect to this example. Here is a bridge circuit, and it is used for sensing things like temperature, pressure, etc. And we assume that this amplifier has a very large input resistance. That means these two currents are 0. The bridge circuit is made up of 4 resistances: RA, RB, RC and RD. Out of these, RA, RB and RC are equal, constant, and that is denoted by R. This resistance RD varies with the quantity being measured, such as temperature or pressure. So essentially this RD is the resistance presented by the transducer that we are using to sense the quantity of interest, such as temperature. So RD is given by R, that is its nominal value, which is the same as RA, RB and RC, plus delta R. Now this delta R varies with the quantity being measured, and typically delta R is small with respect to R, such as 1%, 2% and so on. So delta R is a small fraction of R. Now the whole purpose of this bridge is to convert this delta R into a signal voltage, which can then be suitably amplified and used for display or control purposes, as shown in this figure. So this V2 minus V1 is going to be proportional in some way to the resistance change delta R, which is proportional to the quantity being measured, and therefore the output voltage would be a measure of the temperature or pressure. So that is the broad idea. Let us now see what the signal is going to be. Assuming the amplifier to have a large input resistance, as we said earlier, V1 is R divided by R plus R, just voltage division, times VCC, because there is no current going there. So that is half VCC. What about V2? V2 is RD divided by RC plus RD times VCC. RD is R plus delta R, R plus delta R. This is RC. So let us simplify this now, knowing the fact that delta R is a small fraction of R. So we rewrite this expression as this here: half 1 plus x divided by 1 plus x by 2, where x is delta R by R. So what we have done is we have divided both numerator and denominator by R, and now we want to simplify this further, knowing that x is small, such as 0.01, 0.02 and so on. So 1 over 1 plus x by 2, if x is small, is 1 minus x by 2, and that is what we have written here. So this expression is the same as half 1 plus x times 1 minus x by 2 times VCC. And now when we multiply these two terms, we get 1 plus x minus x by 2 minus x squared by 2. So x squared by 2 is much smaller than x if x is small, and therefore we can ignore it. And then we end up with half 1 plus x by 2 times VCC, where x is delta R over R. Let us take an example. Say our VCC is 15 volts, R is 1K, so that means all of these resistances RA, RB, RC are 1K each. Delta R is 0.01 K, that means RD is R plus delta R, so 1K plus 0.01 K, that is 1.01 K. And now let us see what V1 and V2 are. V1 is VCC by 2, so that is 15 by 2 or 7.5 volts. V2 has two terms. The first term is VCC by 2, so that is 7.5 again. Second term is X by 4 times VCC. And what is X? X is delta R by R. So delta R is 0.01 K, R is 1K. So delta R by R is 0.01. It's dimensionless, of course. So the second term then is X by 4 or 0.01 by 4 times 15. So that turns out to be 0.0375 volts or 37.5 millivolts. So here are the V1 and V2 values again for the example we considered. V1 is 7.5 volts there. V2 is 7.5 plus a small voltage, namely 0.0375 volts, that is V2. Now the amplifier should only amplify V2 minus V1, which is this quantity here, a small voltage, because that is the signal arising from delta R. This 7.5 has nothing to do with the signal or the temperature or pressure being measured, and the signal information is embedded only in this term here. So therefore the amplifier should amplify V2 minus V1 and nothing else. So that is the purpose of this whole setup here. Let us learn some definitions. If we have two voltages V1 and V2, the common mode voltage is defined as the average of the two, half V1 plus V2, and the differential mode voltage is defined as V2 minus V1. The common mode voltage is denoted by V sub C and the differential mode voltage by V sub T. We can also do the reverse transformation, that is, given VC and VD, we can obtain V1 and V2. V1 is VC minus VD by 2, V2 is VC plus VD by 2, and you should verify that these equations are identical to these equations here, the definitions that we considered. In our example, VC is V1 plus V2 by 2, so 7.5 plus 7.5 plus this small voltage divided by 2, and that is approximately going to be just 7.5 volts because that is a small number. So the common mode voltage is 7.5 volts. The differential mode voltage is V2 minus V1, so that 7.5 gets cancelled and we end up with 37.5 millivolts. Note that the common mode voltage is quite large, 7.5 volts, compared to the differential mode voltage, 0.0375 volts. And this is indeed a very common situation in transducer circuits. So it is clear that we are looking for an amplifier which will only amplify the difference between two voltages, V1 and V2. And here is a black box representation of such an amplifier. It has two input terminals, plus and minus, and the two voltages are denoted by V plus and V minus. Such an ideal amplifier would only amplify the difference between these two voltages, that is V plus minus V minus, giving the output voltage VO as AD times V plus minus V minus, that is AD times VD, where VD is the differential mode voltage. Now this AD is a gain, it's a voltage gain, and that is called the differential gain of the amplifier. And we have been simply calling it the voltage gain when we talked about the op-amp. Op-amp also has the same configuration. It has a non-inverting input and an inverting input, and it also has this relationship when it is working in the linear region. But so far we have only called the gain as simply AV, but strictly speaking we should be calling it the differential gain, or A sub D. In practice, the output can also have a common mode component. This component we have already seen, that is the differential gain times the differential input voltage. In addition, there is this common mode component. This is the common mode gain A sub C, and V sub C is the common mode input voltage. So an amplifier in practice will amplify not only the differential mode input voltage but also the common mode input voltage, which is of course undesirable, like we have seen in the last bridge circuit example. So AC is called the common mode gain, and we would like it to be small, ideally 0, because we want to throw away the common mode input voltage. So we don't want to have any effect of the common mode input voltage on the output voltage. And that is where we define a figure of merit called the CMRR, or common mode rejection ratio. The ability of an amplifier to reject the common mode input signal is given by the common mode rejection ratio, CMRR, and that is the ratio of the differential mode gain AD and the common mode gain AC. And of course ideally we would like this to be infinite, because we would like AC to be 0. In practice it may be large but not quite infinite. For the 741 op-amp, the common mode rejection ratio is 90 dB or 30,000. That's a large CMRR. And for all practical purposes, we might consider that to be infinite for several applications. And in such cases, the circuit as a whole may still have a much smaller CMRR, and that is because there could be mismatch between circuit components. For example, resistance values. Some circuits will require two resistances to be perfectly matched, but they may not be because of manufacturing limitations. And in such cases, the mismatch between circuit components will determine the overall common mode rejection performance of the circuit. And we will look at an example of this situation soon. Here is a circuit which serves as a difference amplifier. That means it amplifies the difference between the two voltages and produces an output which is proportional to that difference. We will look at the operation of this circuit, but before we do that, let us ask this question: can we not use the op-amp itself as a difference amplifier? After all, it does produce an output voltage which is the open loop gain times V plus minus V minus, as we have seen earlier, as long as the op-amp is operating in the linear region. So what is stopping us from using that as a difference amplifier? There are two issues. One, as we have already seen, the gain of the op-amp is extremely large, something like 100,000, and therefore that means only very small voltages can be applied here. Very small differential voltages can be applied at the inputs. Otherwise the op-amp is going to get driven into saturation, either positive saturation or negative saturation, and we don't want that. That is one. And the second issue has to do with offset voltage of the op amp, and we will discuss that a little later. So for these two reasons, and there could be more, the op amp itself is not a good practical difference amplifier. Okay, let us now try to analyze this circuit, and we will assume that the op amp is operating in the linear region. There are two ways of doing it. Method 1, the input resistance of the op amp is very large, so therefore I plus is 0, and therefore we can write V plus using voltage division. So V plus would be R4 divided by R3 plus R4 times VI2, like that. Since the op amp is operating in the linear region, V plus and V minus are nearly equal, and therefore this current I1 is VI1 minus V minus divided by R1, and we can write that as VI1 minus V plus divided by R1, because V minus and V plus are nearly equal. Now I minus is 0, that's an op amp input current. And what does it mean? That means this I1 also goes through R2, and that gives us an expression for VO. So VO is V minus minus this I1 times R2. So that is equal to V plus, because V minus and V plus are nearly equal, minus R2 times I1. We already have an expression for I1 right there. So we substitute that and get this result. So we have now got VO in terms of V plus. The next step is to substitute for V plus this expression, and that will give us VO in terms of VI1 and VI2. And in doing that, if we select R4 by R3 to be equal to R2 by R1, then we end up with this very simple relationship, namely VO is R2 by R1 times VI2 minus VI1. So this circuit is serving as a difference amplifier. It is amplifying only the difference between the input voltages, and we can adjust the gain simply by choosing appropriate values of R2 and R1, and of course also making sure that R4 by R3 is equal to R2 by R1. So there is some algebra involved here, so you are definitely encouraged to start with this equation, use this condition, and then arrive at our final result. So this was our method 1, and what did we do in this method? We used the golden rules, that is the op amp input currents are 0 and V plus and V minus are nearly equal when the op amp operates in the linear region. There is another method to arrive at this same result, and let us look at that now. Let's now look at method 2, which is based on the idea that we should not really reinvent the wheel when it's not called for. And let us see what we mean by that. Since the op amp is operating in the linear region, we can use superposition. And this sounds strange at first, because when we think of op amp, we think of a very large gain, we think of saturation and so on. But when the op amp is operating in the linear region, its equivalent circuit is indeed a linear circuit. It has got an input resistance, it has got VC, Vs, and it has got an output resistance, and all of these elements make up a linear circuit. So therefore our entire circuit is actually a linear circuit, and therefore we can use superposition. So let us do that now. We have two independent voltage sources Vi1 and Vi2, and we can take them one by one. So we keep Vi1, deactivate Vi2, and we keep Vi2 and deactivate Vi1. So this we will call as case 1 and that as case 2. And what we can do now is find VO in case 1, find VO in case 2, and then simply add the two. What is case 1? Case 1 is actually an inverting amplifier, and we can figure that out when we look at this voltage here, V plus. V plus is simply 0 here, and the circuit is exactly the same as the inverting amplifier circuit, and therefore VO then is Vi times minus R2 over R1. So we are not really reinventing the wheel here, we are using existing or known results. So that is our case 1. What about case 2? Case 2 is very similar to a non-inverting amplifier, provided we get this voltage, and that is easy to do since this current is 0. This V plus is given simply by voltage division between R3 and R4. So therefore V plus, which is the input for the non-inverting amplifier, is R4 divided by R3 plus R4 times Vi2. So V plus times 1 plus R2 by R1 is VO, because we already know the gain for the non-inverting amplifier, that is 1 plus R2 by R1. So that is our VO2, 1 plus R2 by R1 times R4 by R3 plus R4 times Vi2. This is the gain of the non-inverting amplifier, and the input voltage for the non-inverting amplifier is, as we have seen, this quantity here. And now we can put these two together, and the net result is exactly what we had in the last slide. VO is VO1 plus VO2, and that is our VO2, that is our VO1, and therefore again it boils down to R2 by R1 times Vi2 minus Vi1, provided R4 by R3 is selected to be the same as R2 by R1. And it is easy to see that this will happen. Suppose we take R4 out and R3 out, then we see that this 1 plus R2 over R1 and 1 over 1 plus R4 by R3 will cancel out, and then we get this result here. So superposition is very handy, at least in this case, and you can do things almost by inspection, much simpler than what we did in the last slide. Let us now come back to the bridge circuit. If you recall, we wanted an amplifier which will give an output which is an amplified version of this difference V2 minus V1. And now we have got that amplifier, our difference amplifier. And in this example, we have R2 equal to 10K, R1 equal to 1K, and R3 the same as R1, R4 the same as R2. So the gain of this difference amplifier is R2 by R1, which is 10K by 1K, or 10. So VO then is V2 minus V1 times 10. So we seem to have got the solution we were looking for. But there is a problem, and let us see what that problem is. When we connect the amplifier to the bridge circuit, we expect that V1 and V2 stay the same as before. And when will that happen? That will happen if the amplifier does not draw any current from this bridge circuit. Or in other words, we expect the amplifier to have a very large input resistance compared to all of these resistances. Now that is not happening in our difference amplifier, and let us see why. The resistance seen from V2, this resistance here, is R3 plus R4 because that op amp input current is 0. So therefore all we see is R3 and R4 in series. And in this case it is 10K plus 1K or 11K. Now 11K is not too large compared to this 1K or this 1K. And therefore our V2 is going to get disturbed, and that of course is not desirable. So we definitely need to improve the input resistance of the difference amplifier. And we will discuss an improved difference amplifier later. But before we do that, let us discuss another problem with the above configuration, above difference amplifier, which can be important for some applications, and that we will do in the next slide. In summary, we have looked at the meaning of common mode and differential mode voltages and considered a bridge circuit to illustrate these ideas. We have seen the importance of the common mode rejection ratio, or CMRR in short. After that, we have looked at an op amp circuit, the difference amplifier, which can be used to amplify the difference between two input voltages. In the next lecture, we will discuss why this circuit needs to be improved. Until then, goodbye.